So it looks like we have the two speakers, and we're trying to find, I guess, several pieces of information. First of all, we're going to need to figure out what is the phase constant, or what is the difference in phase constant, and where are we going to hear maximum volume. So looking for where we would find constructive interference. And then also looking into Doppler effect if the listener is moving. So to start with, we are 3 meters away from speaker A and 12 meters away from speaker B. We also know the frequency, 42.5 hertz. So just listing out what we know, frequency is 42.5 hertz. And if you're standing at this location, wave 1 or wave A is traveling 3 meters. So let's call that XA. And then wave B is traveling 12 meters to get to your location from 15 minus 3. So what would be delta X here?
It depends how you define it, but I said 9 and I did it just B minus A.
Yeah, so XB, and yeah, we can definitely subtract in either order. We just want to choose an order and be consistent about it. So let's say we are subtracting, and I'm going to make a note of that elsewhere just as a reminder. We are using delta equals B minus A. Because we want to make sure we are consistent about the order we subtract. And that's really why in part A, it says be sure to specify whether delta phi is phi A minus phi B or phi B minus phi A. We want to make sure we're consistent about that. Because if you reverse the order, you get the opposite value, just a plus or minus thing. So we know the frequency, we know delta X, and we also know that you're hearing destructive interference. So what does that tell you? What equation can you set up if you know it's destructive interference?
If it's destructive, then we know there has to be, or we know that the full delta phi, like the big delta phi, equals 2n plus 1 pi.
Yeah. So let's start with that. We can write out the total phase difference. Using the usual total phase difference equation. We've got the time and frequency term, the position and wavelength term, and or distance traveled in wavelength, really. X isn't so much about position, X is about distance traveled, and possibly a delta phase shift term. And we know delta total phase must be an odd number times pi, or 2n plus 1 times pi, because it's destructive. So that's something and a half complete cycles. And what can we fill in here? What values do we know?
So we have the frequency, and then also because we have velocity and frequency, we can find the wavelength.
Yeah, we know that speed equals wavelength times frequency. So wavelength is going to be speed over frequency. What speed should we use here?
340.
Yeah, these are sound waves, and speed of sound given here is 340 meters per second. So we take that and divide by the frequency, 42.5 hertz. And what does that give us? 340 divided by 42.5, 8 meters. So the wavelength is 8 meters. If we fill that in here, by the way, what should this 2 pi t times delta frequency term look like when we fill in values?
I believe, well, the end, maybe this is what you're asking, but the end result ends up cancel. Like it'll end up being 0.
Yeah, because Right. They're the exact same frequency, so there's no difference in frequency. And there's no difference in time either. I mean, formally, we would probably say delta time times frequency. But both waves are arriving at your ears at the same time, and they both have the same frequency. So this entire term is 0. And also, since these both have the same wavelength, wavelength can be factored out of the delta. Any constant multiplier or constant divisor can be factored out of a delta because delta is just subtraction. We now know the wavelength, 8 meters, and also what's delta x. Yeah, it looks like that's going to be 9 meters. So we can fill in, because we subtracted xb minus xa, 12 minus 3, that's 9 meters. So we got negative 2 pi times 9 meters divided by 8 meters, plus possibly some unknown phase difference equals an odd number times pi. And if we simplify that, we've got the 2 and the 8 reduced to 1 over 4, so we get 9/4 times pi. Oh, that should be negative, actually. Negative 9/4 times pi plus delta little phi equals 2n plus 1 pi. Any questions on that so far? And looking at what we have at this point, is this an odd multiple of pi? Is negative 9/4 an odd number? Because ultimately we want an odd number, right? We want this to be odd number times pi. But yeah, negative 9/4 is not an odd number. This is not an odd number times pi. So this term alone would not create destructive interference. In fact, if this were the only term in the whole thing, what sort of interference would that lead to? Yeah, this term alone, the not a whole number times pi, this is not a whole number of cycles. It's also not something in half cycles. So this term alone, just what we get from just the distances, suggests partial interference. This is ultimately why we need another term to turn the whole thing into destructive interference. Without a phase difference, we'd just be getting partial interference here. You'd hear some sound, a little bit. But to get destructive interference, you need this extra term to make it some odd multiple of pi. So we need to figure out what we have to add here to turn negative 9/4 pi into an odd number times pi. And there's actually infinitely many values you could use for delta phi, because we just need these to add up to any odd number times pi. But we probably want to choose a delta phi value that's the simplest we can possibly get, the easiest number we can get to work with. So how could we accomplish this? How could we solve for delta phi here?
So what I did is, just to make it easier, I multiplied the pi into 2n plus 1, so it's just distributed. And then then it's like, I don't know, it's easier to look at. And then I, continuing kind of the basic algebra, I added the 9/4 pi to the other side.
Yeah, so that would give us delta phi, little phi, equals 2n times pi plus 9/4 times pi. And then if you combine those, what's 1 pi plus 9/4 pi?
That's, I wrote 13/4, but I think that's not, is that right?
No, that should work because we have 1 pi. 1 is 4/4, and then we're adding 9/4, so we get 13/4. So 13/4 times pi. And then we have to add the 13/4 pi plus any even number times pi. So we could use any even number we want here. And any even number will work, but it's usually a good idea to make delta phi as close to 0 as possible, positive and close to 0, if possible. I mean, it should always be possible, but you want to make it close to 0 to make the number easier to work with. So what even number could you use? What even multiple of pi would lead to this being close to 0?
Can you use 0 for n?
We could say let n equal 0. Then we get delta phi equals 13/4 times pi. So 13/4 times pi is certainly a value you could use. But it might be easier to use a smaller value of delta phi. What would be a lower n value we could use?
Maybe I ended up, I think this is what you're saying. I ended up saying that delta phi equals 5 pi over 4.
Yeah, that would work. And that's ultimately just by using, well, here we used 0 for n. What's the next whole number less than that?
-1?
Yeah, if we use -1 for n, then we get an extra 2 times -1 times pi plus 13/4 pi. That's -8/4 plus 13/4. So that becomes 5/4. So 5 pi over 4 would be our delta little phi here, our delta phase shift. And note that that's assuming we're subtracting b minus a. If we were subtracting a minus b instead, you'd get -5 pi over 4. And honestly, you can use any n value, any whole number, any integer, I should say, for n will give you a delta phi that will work. But to make the numbers easier to work with, I would choose an n value that makes delta phi as close to 0 as possible. And -1 works here because if we had gone to -2, which again you could do, you get -4 pi plus 13/4 pi, which would lead to -3 pi over 4. And by the way, how far apart are those two values that would work? What's the difference between 5 pi over 4 and -3 pi over 4?
2 pi?
Yeah, exactly 2 pi offset from each other. And the 13 pi over 4 we were looking at earlier is 2 pi away from that.
So when writing the answer for this, would you, because my understanding was that you would ultimately want your answer to be between 0 and 2 pi. So do you have to write both 5 pi over 4 and -3 pi over 4, or just?
Well, you could use any one of them really. I would probably use 5 pi over 4 because that one is between 0 and 2 pi, whereas -3 pi over 4 is not. But any of these will still work mathematically. It's just customary to use the one between 0 and 2 pi.
Okay, got it. And you're just showing the other one just to say as it's a possibility.
Yeah, you could use 5 pi over 4 or -3 pi over 4 or 13 pi over 4 or 29 pi over 4.
It's just that 5 pi over 4 is the most correct.
I don't know if I'd even say most correct. I'd say probably most useful, maybe. That it's probably going to make the next steps easier. And of course, if you're subtracting the other order, if you're subtracting a minus b, you'll just get the opposites of all these. So you could use -5 pi over 4 or +3 pi over 4 or -13 pi over 4 and so on. And how do we get two phase constants? The only one from n equals -1 was the 5 pi over 4. So 5 pi over 4 is what we get if we use n equals -1. These other ones were for other n values. So -3 pi over 4 would be if we used n equals -2. 13 pi over 4 was if we used n equals 0. 29 pi over 4 would be if we use n equals +1. So different n values lead to different values of delta little phi. Again, they all still work because the choice of n is kind of arbitrary. But the one that's closest to, the one that's between 0 and 2 pi is the customary one to use. partly just because having a standard for that means everybody gets the same result, so it's easier to compare results, but also because small positive whole numbers or small positive numbers are usually easier to work with. And we're going to need this in the next step. Any other questions on the calculations behind that so far?
Wait, sorry, one more. What n value did you use to get the -3 pi over 4?
That would be from using the next n value less. So that would be n equals -2.
Okay, thank you.
And if you're not sure, you can just like try 0 and see if that gets you a good result. If it gets you a value that's too big, try using -1, -2, or if you want to go the other direction, +1, +2. You can also kind of tell from looking at this earlier, we had a 13 pi over 4. That's too big on its own. We want to make that smaller. So try using a negative value, a small negative value for n to cut that down to a smaller size. Specifically -1, because I noticed that -1 make this -2 pi becomes 8 pi over 4 negative, which cancels out most of this, but not all of it. So -1 would, I think, be the most useful n value to use here. So we now have delta little phi equals 5 pi over 4. So we'll use that for our next calculations. Any other questions on that part? And up next, we want to figure out where would we hear a maximum volume. So in this same setup, where suggests we're allowed, or at what location suggests we're allowed to move around. So instead of having this location, let me clear that out. Instead of being at this location, let's say you could be anywhere. Let's say you could move to a new location. Doesn't even have to be at a whole number mark. You could be moved to anywhere you want. And let's say you're at this new location. So you've got XB and XA. Of course, XA won't be 3 meters anymore and XB won't be 12 meters anymore. What we want to do, though, is we want to set up a variable here, because ideally we'd like to be able to turn this whole thing into an equation we can solve for some distance. Since these distances are already marked in terms of XA, in terms of this chart here, I would use XA as the variable. Or let's make up a new placeholder variable. Let's say XA equals L, some length that you're standing away from A. So let's say L is just the length from speaker A to your location. In that case, what would XB look like? Can we write XB in terms of L?
Be 15 minus L, maybe?
Yeah. Because if the total distance between speakers is 15, you've got L away from one of them. The leftover distance would be 15 minus L away from the other. 15 meters minus L. So XA is L, presumably measured in meters. XB is 15 meters minus that distance. So to find delta X in this new situation, we would take, and we want to subtract in the same order to be consistent, B minus A, XB minus XA. Subtract those, and what do you get when you simplify?
It's like 15 minus 2L.
Yeah, 15 meters minus 2L. So that would be the difference between these two lengths. The difference between how far wave A travels versus how far wave B travels, that difference is 15 meters minus 2L. Any other questions on that so far? So using that, let's try using the exact same delta total phase equation. With some changes. Instead of 9 meters as delta X, we're going to have this 15 meters minus 2L for delta X. So that's our time term doesn't matter because we're still having waves arriving at the same time and they both have the same frequency. So we just got negative 2 pi times delta x, which we don't know, but we can write in terms of L, divided by the wavelength, 8 meters, because it's still the same wavelength, plus delta phi. But what do we know about delta phi now?
We found the value from the previous question, so it's
Yeah.
5/4.
Exactly. And this is really why we needed that piece of information. We needed to know something about what type of interference we get at some location so we can solve for delta phi and use that in the arbitrary anywhere you could stand. Also, we want constructive interference. So what should we put on the other side of the equation here?
2 pi n.
Yeah, exactly. 2 times some whole number times pi. That is an even number of pi or a whole number of cycles. So 2n pi, a whole number of cycles. And it looks like other than n, which just has to be some whole number, the only unknown here is L. So we should be able to solve for L here. Also, before we even get started, what shows up in every term here?
Pi.
Yeah, so let's divide both sides by pi to simplify that. If we divide both sides by pi, we can cancel out a pi from every term. Cancel out a pi from the distance term, cancel out a pi from the phase shift term, cancel out pi from the total phase. So we're left with negative 2 times 15 meters minus 2L divided by 8 meters plus 5/4 equals an even number, 2n. And then how would we start solving for L here?
You'd first subtract 5/4.
Yeah, may as well subtract 5/4 from both sides.
And then it looks like you multiply by -4, just because it's kind of -1/4 on
Yeah.
the.
Yeah, that would be a good idea. We can reduce that first because we've got 2/8. That reduces to 1/4. So if we multiply both sides by -4, that cancels out the negative and the times 4. So 15 meters minus 2L equals -4 meters times 2n minus 5/4. Also, I think it might be useful to multiply both sides by -1 here, just to reverse the order on the subtraction. So multiply both sides by -1, we get 2L minus 15 meters equals positive 4 meters times 2n minus 5/4. And then what?
Should distribute the 4, so, or I would distribute the 4, so 2L minus 15 equals 8n minus 5.
Yeah, or 8 meters times n minus 5 meters, because we want to keep the units as well. And then to finish that off, we can just add 15. Add 15 meters to both sides. So 2L equals 8 meters times some whole number, minus 5 plus 15 is plus 10 meters. And then what would L end up being?
So I think we do the same thing where we want to the lowest n possible. So,
well, before we do that, what else do we need to do to isolate L?
Oh, divide by 2.
Yeah, divide by 2. That applies to both terms because of the distributive property. So 8/2, 4 meters times n, 10/2, 5 meters. In other words, L is any whole number multiple of 4 meters plus 5 meters. In this case, though, we can't just look at finding the smallest value for L, because we want to find all the locations where you hear a maximum volume. So that means we want to look at all possible n values. Of course, there's infinitely many n values, but we just need results that are in what range? What's the lowest and highest L could be?
Between 0 and 15.
Yeah, we were assuming that the location you're standing is somewhere between the speakers. If you go outside the speakers, that messes up the equation and we'd have to write a different equation instead. But as long as you're between the speakers, L has to be between 0 and 15. So we need to restrict our search to just L values between 0 and 15. So let's try making a chart here. If we just make a chart of N versus L, what are some N values we could use here? What would be the easiest N value to plug in?
Well, the easiest is 0, I think, but the first one is -1.
Yeah, although I would usually start with 0, and then if the 0 looks like it's somewhere in the middle, try progressing outwards in both directions. And if you can immediately see what N values are going to lead to the furthest or the closest, then go ahead and use those. But if you're not sure, I would generally recommend starting with 0 and then progressing from there. Like if we plug in 0 for N, what do we get for L?
5.
Yeah, 5 meters. And that is a permissible location. 5 meters is one of the locations between the speakers. So let's keep going. You plug in, let's say 1, and what would you get for L?
9.
Yeah. And 9 meters is also allowed. Let's keep going. What about 2?
13.
Yeah. And 13 meters is still in the range. What if we plug in 3?
17 is outside the range.
Yeah. So we can ignore that one. And of course, anything beyond 3 is just going to be further beyond 15 meters. But as you said, 5 meters is not all the way at the other end yet. So let's try negatives as well. If we plug in -1 for N, what do we get for L?
1.
Yeah, 1 meter. And that's in the range. That looks like it's at the edge, but just to be on the safe side, let's check -2. Plug in -2 for N, and what do you get?
-3.
Yeah, and that is also outside the range we're discussing. So that's out. So it looks like there are 4 locations in this region that will allow you to hear the loudest possible sound. 1 meter, 5 meters, 9 meters, and 13 meters. Any other location will not be perfectly constructive interference. Any other questions on that one? Or any other general questions or topics you'd like to get some more practice on?
Could we maybe do one of the graph ones where you're given a y of t and y of x, and then you have to determine the direction?
Oh, for the wave?
Yeah.
Maybe. Let me see what we have here.
I can try to find one as well.
Okay. And Snell's law and film thickness. Yeah, let's try one with the thin film thing, because that involves, well, that's more interference, I guess. Was there something particular on Snell's law you wanted to try out? Were there some other practice problems here that would work for that? For Snell's law, the main thing you would use that for is if you have light traveling from one material to another. So in general, anytime you have, like, let's say you have maybe a body of water, a rectangle of water, and you have light passing from air to water. The main use of Snell's law here would be to figure out, as the light travels from air into the water, how does its direction change? So to figure that out, you draw in a normal line, just a line perpendicular to the surface at the location of where the light hits the water. And then you'd measure the angle that the ray of light makes with the normal line. So that is the theta in Snell's law in the equation, or θ1, let's say. And then what's going to happen to the light as it passes through? Yeah, it's going to refract, which essentially means it's going to bend. instead of going through in a straight line, which would make the same angle, we're going from air to water. What's the important difference between air and water here?
They have different indices of refraction.
Right, different indices of refraction, which is ultimately all about speed. High index of refraction means a slow speed of light. Lower index of refraction means a higher speed of light. And would you expect light to travel faster in air or in water?
Air.
Yeah. In air, light is traveling faster. In water, light is traveling slower. Still pretty darn fast, but slower than it does in air. So we have decreased the speed. Light is going towards a medium with slower speed. And if the speed is decreasing, that means the angle will also decrease. Instead of getting the same angle, it's going to bend to make a smaller angle. So we would also describe that as bending towards the normal line. It bends in a way to make the angle smaller. So this angle measured from the normal line, as always, would be theta 2. And Snell's law is really all about finding how much it bends, how much that angle is going to be. So we would say the usual n1 times theta 1 equals n2 times theta 2. So using the index of refraction in order to predict those angles. Any questions on that so far? And in general, if you're looking at light traveling from one medium to another, you use Snell's law to figure out how the angle changes. If light's traveling just within one material, like let's say this light continues traveling in water for a while and then hits something else. Within the water, it's traveling in a straight line. So you can use geometry to figure out any other angles that it encounters. Let's also take a look at that thin film that was mentioned earlier. The idea is if you have, let's say you have water and air, but in between you've got some other medium. Let's say a thin layer of oil. And that's relatively thin. I'm going to draw it kind of thick so we can see what's going on in between. So let's say in between is oil, which is, let's say, a medium speed light. Let's say kind of slow. So we're going from very fast light to kind of slow light to much slower light. What's going to happen when we shine light on this, if you've got this incoming ray of light, what happens to this incoming ray of light when it hits the oil?
It'll bend towards the normal.
Yeah, although in this case, we're not really so much concerned about the bending. And in a case like this, we're typically assuming it's pretty much just going straight in. Some of it does go through and bend, but not all of it. Because the ray of light actually splits when it hits a material separation like this. I mean, not just for the oil slick on top of water, but in general, anytime light hits a new material, usually we expect some of it to go through and some of it to bounce off. So what's going to happen here is we get a split beam. Some of the light gets through, some of the light bounces off. But the light that gets through, what happens to that light?
It's like a similar thing happens again where part of it reflects and part refracts. Or...
Yeah, some of it gets through and some of it bounces back up. And then when that hits this, some of it bounces back, some of it goes through. But let's just assume for the moment that all of it gets through, because what we really care about is the light that actually reaches the observer's eyes. So let's say the light reaches the eyes of some observer. Let's say you are standing up here looking at this light from above. So here's you standing up here. Let's say this is the eye. And the light reaches the eye. So both of these beams of light reach the eye, but you're going to get some interference here because what's the main difference between these two rays of light?
They're reflecting off at different points.
Yeah, these are reflected off of different pieces. As for the n values, we don't really need to know the n values here because we're not really looking into how it bends in this case. If we did want to know how it bends, we would need all three n values. But in this case, we're just looking at the bounce back. This bounce back is going to be, since it's bouncing off of different surfaces, these waves travel different distances. One of the waves travels this far, and then this far. So that's traveling a certain distance. The other wave travels this far and then this far. So these two rays are traveling different distances. They are different path lengths, which means we get interference. And depending on the wavelength, some wavelengths, therefore some colors, will become constructive interference and look really bright. Other wavelengths are going to become destructive interference and not be seen at all. So you only see certain colors bouncing back because those wavelengths lead to constructive interference. And to determine which wavelengths, let's say we call the thickness of the film, let's call that thickness distance D. Capital D equals thickness of film, the thickness of this thin film of oil. Then how much further is the green ray traveling in terms of D?
2D.
Yeah, it's traveling an extra 2D. The extra distance traveled by the longer ray is 2D because it goes 1D on the way down that the other wave didn't, and also an extra 1D on the way up that the other wave didn't. So delta X equals 2D, 2 times the thickness of the film.
Does it matter that technically because they're at an angle, they're traveling greater than D?
The angle is basically just to make it easier to see what's going on. Realistically, I think we're assuming that the light goes straight down and bounces straight back up.
Okay, that makes sense.
Also, the thing is, since this is a very thin film, even though they're even if they are at an angle, these two rays are basically parallel. They're traveling essentially the same path, except one of them has traveled a little bit extra. And it's kind of difficult to see that with the exaggerated thick film. But if you assume the film is very thin, then these two portions of path are almost the same anyway. But you could now set up an interference equation, the total phase difference equation, exact same total phase difference we were looking at earlier, except the delta X would be 2D. And then you could solve for D, the thickness of the film. For instance, if you know the wavelength, like let's say you look at this and you see a certain color of light reflected really strongly, you could set lambda equal to the wavelength of that color of light and set the other side of the equation equal to even number times pi because it's constructive, and then solve for D to figure out the thickness of the film. Or alternatively, if you know the thickness of the film, you could solve for lambda to figure out what colors of light you will see reflected. And this is actually why if you have, let's say you've got oil floating on water, it's not all going to be the same thickness everywhere. You're going to have ripples and the thickness is going to fluctuate from location to location and from time to time. If the thickness changes, that changes which wavelengths of light will be constructive interference. So what would you actually see there? What do you usually see if you look at a thin film of oil floating on water? What does that look like? Yeah, you see a rainbow pattern. You're seeing this gradient of different colors, and each color corresponds to a certain thickness because each color is a wavelength, and different wavelengths reflect back constructively with a specific thickness of film. So if you've got oil with different thicknesses, like let's say you've got sort of almost a wedge shape, thin on one end, thicker on the other, then each thickness is going to reflect a different color of light. If you've got a continuous transition from thin to thick, you get a continuous transition from one color to another across the rainbow spectrum. So this is the physics of what causes those rainbow patterns in oil slicks on water, in soap bubbles, in certain situations with like a thin coating on a window or sunglasses, Rainbow reflection effects are caused by this sort of thin film interference. And the different colors you see are essentially a color map of the thickness of the film, each color corresponding to a certain thickness. Any other questions on that?
So what type of question, what would we have to solve for in this kind of question?
My guess would be something like you have the thickness of the film and you're trying to find what wavelength, what color reflects off of it with constructive interference. Or you know the wavelength that reflects off with constructive interference and you're trying to solve for the thickness of the film. Either way, you would set up the total phase difference equation like we did earlier, except the only difference would be you'd replace delta x with 2d.
So it's not the d sine theta over n lambda?
No, because this is not a double slit situation.
Oh, right. So it's the same type of basic equation that we did for the question we just worked on, right?
Yeah. Any sort of interference, you can always use the total phase difference equation. The time and frequency term plus the position and wavelength term plus delta little phi equals delta big phi.
So how does
sorry, what was that?
Sorry, go ahead.
I was going to say that works for any interference problem. It's just that some specific situations have a variation on that formula. Like the d sine theta equals n lambda from double slit experiment. That's ultimately just using or combining the interference idea with the specific geometry of that situation.
Okay, that makes sense. I was just going to ask, where does d fit into that equation?
In this case, it would be the delta x, because delta x is 2 times the thickness of the film, since you get an extra distance on the way down and the same extra distance on the way up. So 2 times the thickness.
Oh, right.
And
okay.
So in your total phase difference equation, you've got the 2 pi times delta x over wavelength. Delta x is 2d here.
Okay, and then one more question just to confirm. So like when the magenta line, or like for example reflects off the oil, the angle is the angle from that line to it's not perpendicular, but like the horizontal line is the same for the initial ray and the reflected ray, right?
If the ray is being reflected, then the angle doesn't change at all. And we usually measure the angle from the normal line rather than from the surface. But either way, the result is the same in this case. So if you draw in a normal line at that point, the angle of the ray coming in with the normal line should be the same as the angle of the reflected ray made with the normal line. And that's ultimately because you're not changing medium. The incoming ray starts in air. The reflected ray is also in air, so there's no change. Likewise, for the ray in the oil bouncing off the water, you've got a ray that starts off in oil, and then it bounces off and it's still in oil, so the angle hasn't changed. You would generally only expect the angle to change if you're changing from one medium to another.
Will we ever have to know, like, or I mean, at least for tomorrow or this class, I guess, like what percentage is being reflected versus refracted?
I'm not sure. That's a property called, I think it's called reflectance or reflectivity or something like that. I've never seen it really brought up in 7C before. I think somebody had one question on it earlier this quarter, but it's literally just the percentage of light that gets reflected. So like if the reflectance is 0.7, that means 70% of the light gets reflected and the other 30% passes through as refraction.
Okay, but we would never, or I mean, as far as you know, we would never have to like determine the
Yeah, I don't think so. I would guess you wouldn't need to. The only thing that usually in cases like this, we usually assume that either it all gets through or it all bounces off. So we're focusing on just one or the other of those.
It'll probably specify that in the problem.
Yeah, I would expect so. Yeah. All right, I've got to get going, but best wishes on the midterm, and feel free to email me if you have any other questions, and I will see you next time.
Thank you.
You're welcome.